Does AI transform short-circuit current calculation and circuit breaker selection in electrical systems? AI has the potential to significantly improve the process of short-circuit current calculation and circuit breaker selection in electrical systems through the following ways. AI can analyze complex electrical system data and perform accurate short-circuit current calculations, taking into account various parameters and factors that affect the current flow. This can help in determining the appropriate rating and settings for circuit breakers. By utilizing machine learning algorithms, AI can learn from historical data and identify patterns in short-circuit events. This can help in predicting potential short-circuit scenarios and taking preventive measures to avoid system failures. AI can automate the process of circuit breaker selection by considering factors such as fault current levels, system impedance, and coordination requirements. This can save time and improve the efficiency of the design process. Through continuous monitoring and analysis of system performance, AI can detect abnormalities or faults in real time and trigger appropriate actions, such as tripping circuit breakers to isolate faulty sections. This can enhance the safety and reliability of electrical systems. AI can also assist in optimizing the placement and configuration of circuit breakers in a system to minimize the impact of short-circuit events and improve overall system performance. Machine learning is a promising approach for short-circuit analysis in modern distribution grids. Feature engineering is important to enable effective training with minimal data. Online prediction from trained models enables real-time applications. Here is a sample short-circuit current calculation and circuit breaker selection for an electrical system. Given 1000 kVA transformer with 5% impedance, 480 volts secondary voltage. Fault occurs on the secondary side. To calculate short-circuit current, 1. Base values. S base is equal to 1000 kVA. V base is equal to 480 volt. 2. Transformer impedance. Z is equal to 5%. Z per unit is equal to 0.05 per unit. 3. Calculate fault impedance. Z fault is equal to V base S base x Z per unit. Z fault is equal to 480/1000 x 0.05. Z fault is equal to 0.024 ohms. 4. Calculate fault current. I fault is equal to V base Z fault. I fault is equal to 480.024. I fault is equal to 20,000 ampere. For circuit breaker selection, we need to size the breaker to safely interrupt the calculated fault current. Common practice is to select a breaker with an interrupting capacity about 25% higher than the fault current. In this case, we would select a 25K circuit breaker to protect the 1000 kVA transformer secondary at 480 V. This provides a safety margin over the calculated 20K fault current. The specific circuit breaker can be selected based on voltage, current, and other parameters from manufacturer datasheets. This demonstrates a basic method of using short-circuit current calculation to size and select circuit breakers for an electrical system properly. AI and machine learning techniques could automate this process for improved efficiency. Does AI transform short